Good morning, folks. I just want to welcome you to the internet. This thing just might catch on. I don't know though. I can't predict these things. So anyway, I want to welcome you to my secret recording location somewhere located in the foothills of the White Mountains in the New Hampshire, the state of New Hampshire. And again, I would apologize for the mess around here. It's just, you know what happens when you have Robert Downey Jr. over for a party. Anyway, so let's talk about the rest of this chapter 19. Not too much going on for the rest of this. When we talked yesterday, there was a lot of similarities in a lot of the mechanisms that we discussed. So again, there's going to be more of the same, a little bit. I want to focus a little bit today more on the meta positions of things. For these substituents, depending on what substituents you have on the benzene ring, you will have some meta direction. Okay, so let's just get into that a little bit. Okay, we talked about this yesterday. Our discussion yesterday was a really great discussion. We talked about several options on how to attach this alkyl group to this benzene ring, not just with Friedel Crafts, but with some Diels-Alder chemistry and some Grignard chemistry. It was really a great session. So I do please, I do urge all of you to please, make yourself available to come to as many discussions as possible. Okay, every one of them is different. Okay, all right. So let's just get into this. All right, so for deactivating groups, so we talked about activating groups as being ortho-para directors and things like that, and so for deactivating groups, it's about what you'd imagine. Again, they're gonna more direct meta, not ortho and para, and for the sake of our discussions for the next few slides, we'll talk about the nitro group. The nitro group here is a really popular electron withdrawing group here that is wonderfully deactivating. And very, very, very much so meta-directing, okay? And it's just a really easy thing to talk about, but the nitro group will represent a lot of the meta-directors that we talk about for the next several slides, okay? So we'll talk about that. So the nitro group is electron withdrawing through both resonance and induction. Explain how, hint, draw the functional group, and show some formal charges, and we will. Withdrawing electrons from the ring deactivates it. How? We talked about that a little yesterday. When you activate a ring, when you activate the benzene ring, you infuse it with some electron density, so it's little pairs of electron arms, pair of pi bonded sort of arms can reach out and grab that electrophile and drag it back to be attached to the ring. If you withdraw electrons from the ring, it deactivates it. It makes those little pi electron arms pretty weak. Okay, and will withdrawing electrons make the transition state or intermediates less stable? Well, it depends on which ones you're talking about, okay? And that's specifically what we're going to be trying to illustrate here. Okay, so for deactivating groups here, they will not have ortho and ortho and para attacks here. They do not direct ortho para. Why? Because remember before we talked about donating groups here having this localized this local carbocation charge right next to a electron donating group that makes it so stabilized. Having this plus charge here right next to this nitro group here, the end from the nitro group also having a plus charge. When two like charges are adjacent to each other, that really, really, really destabilizes the whole business. And so this guy here is not a very favorable thing to have. So this is going to destabilize the thing there. This here, in the sense of when comparing to the electron donating groups here, right? Here's the ortho attack. Here's a para attack. Notice again, in the para attack, you still have that same sort of like adjacent carbocation next to what would be the positive charge of that nitro group. This is also not very good. Again, we never want to have two like charges next to each other. Again, that's pretty terrible. All right. So the ortho is out and the para is out. So what we focus on here is the meta. All right. And so how can the meta, with none of its favorite things here, be at all something of a favorable interaction or have a set of favorable transition states here? Okay, so how can we think about this? Well, first off, let's look at where this double bond is here compared to where the nitro group is here. Okay, so when we really explode the nitro group here and we have a double bond next to it, you will see that they will have some sort of conjugation. Let's just draw this out really quick if possible. Okay, let's draw a regular nitro group here. All right, on our benzene ring here. All right. I do apologize for my drawing here. It's a little bit hard to draw. Nice straight lines on a tablet, but anyway. All right, so there's that, and I'm going to draw out the nitro group, right, in its entirety. I also want to apologize for how I'm dressed right now. It's not just, age appropriate, age inappropriate. It's just blatantly inappropriate. I don't want to go into it. I'm just saying, you would not think very well of me about how I'm dressed right now. It's something. It's creative. It's, again, inappropriate. And not just wildly inappropriate, but like comically inappropriate. Anyway, I'll get back to what I'm trying to draw here. All right, so there's your positive charge on your nitro group right there. There's your negative charge over there, okay? That's why, remember, we can't have that positive charge right here on those different resonance canonical forms, because if you have a positive charge here, it's adjacent to a positive charge on that nitrogen. Not cool at all. But if we have a positive charge next to it, now that might not be too bad. Now, so as it is, the nitrogen here and the nitro group here in general is a very electronegative moiety right there. They are more electronegative than carbon, which means that we will be drawing electron density. If you had to draw this thing in some sort of a weird, weird like vector, sort of a dipole moment sort of a formalism, you'd have to draw the dipole definitely going this way, right? Definitely, because this guy here is a more electronegative than carbon, so it's all going to be going that way. So you're pulling electron density away from the ring here, making the ring less electron dense than it is right now. Okay, so you're pulling that away. All right, obsessing about that bond for some reason. So let's draw. So this is why inductively this is actually electron withdrawing. Okay, just by induction it is just pulling electron density away from the ring towards the NO2 group here. Okay. Now how about by resonance? By resonance, can we also have that same argument? Absolutely. All right. Draw the same exact thing there. Nitro there. All right. It sort of looks like a crazy 4-year-old is drawing these things. But please, if anybody's watching over your shoulder, please tell them I'm not a crazy 4-year-old. Sometimes I act like a crazy 4-year-old, but this is not one of those. I'm trying to not act like a crazy 4-year-old at this time, but just doing my best, just trying to get by, right? All right. So here's your induction effects here. This is your induction. This is terrible. All right, induction, and here's my resonance. That's crazy. All right, so zoop. Special effects by Lucas by DreamWorks. Okay, so let's just draw this guy here. Now look what we have. Again, this is just through resonance, right? So this is going to be pretty good. All right, so I'm going to drag this whole thing right out of the ring, right there. Okay, still going to maintain the positive charge on that nitrogen. Eek. You know what I'm talking about, right? I'm making it worse. I can't stop it myself. Okay. Negative charge there. Negative charge there. There. Carbocation right there. So do our charges all kind of balance out? Absolutely. Positive, negative. It's all still charge neutral, but this is one resonance. This is one resonance canonical form of the nitrobenzene thing. Okay, this is why this is a deactivating group here. It again draws electron density out of the ring through induction and through resonance. That's why when we have some groups that we want to add on to this thing using electrophilic aromatic substitution, we can never really. This guy here can't direct ortho-para, right? Because imagine this guy here directing ortho at this point. So ortho is right here, right? So imagine this guy here swinging out and grabbing something here ortho. You'd have a carbocation right there. That is not going to be good at all, right? Because ideally, you'd like to have some sort of a way to put a positive charge adjacent to these guys here. Okay, the positive charge would be either here, or here when you have a meta director. Okay, let's look at a few examples, and then we'll go back to doing some more terrible drawings. All right. And so let's go. Yeah, okay, all right. And so and then while we're talking about all this, let's talk about the exception too. Okay, halogens. The exception. Halogens are electron withdrawing groups, but they are also orthopara directors. So they are electron withdrawing groups, and so they are deactivators. They do deactivate, but they direct orthopara. Okay. So that's how it normally that's how it goes for the halogens. Why do they direct orthopara? Right. Well, they deactivate by induction, but they donate electrons through resonance. Okay. Remember when you have some lone pairs on those on that group, right, in the benzylic position, if you can dump electron density into the ring, you will do that because because it is just, again, just another type of resonance. If you can draw a resonance form, no matter how terrible it is, if you can draw one, it's possible. It's just another canonical form, all right? And so that's why you can have halogens being the exception to the rule, because while they are more electronegative than carbon, clearly, they do have lone pairs on them, okay? And again, we'll do some problems here, okay? So these are just this is just showing you that halogens direct ortho-para. Okay, so here is your, we're using chlorobenzene here. Here's your ortho attack here. So this is right from your book. I don't like it how they use nitro group here, but this is going to get confusing. What we're talking about is the directing effects of chlorobenzene. Don't lose sight of that. Even though you see a nitro group here, we're talking about this guy here being the director. Okay, so this guy here directs ortho and para. Okay, not meta, or not meta in any usable sense. Maybe 2 or 3%, but not in any usable fashion. Okay, this guy here can swing on out, grab this nitro group right there. You have a carbocation right there, which undergoes all of its little resonance here. Okay, there. But the most important one of the more important reasons why this thing directs orthopara is because you have the availability of lone pairs on that chlorine to be able to stabilize this adjacent charge right there. Okay, so that's pretty cool. Now they have this weirdly drawn here, but you can easily see between here and here. You can also see very clearly that you can draw a resonance arrow. Okay, between this guy here and this guy here. To not make it so confusing. They push this around the ring for some reason to show you the resonance forms, which are all important. I'm not going to argue there, but again, you don't have to go through all these resonance forms to show that this is going to be so stabilized. If you have a lone pair of electrons next to a carbocation on your ring like this, then this is the most important one. And if you want to show the other ones, fine, right? But this just shows you that you have lots of resonance structures, and it is very stable. But this is also one of the more important resonance canonical forms right there here. Same with the para for the same exact reason. All right. So you can draw this guy being stabilized, this guy here being stabilized like this, again, because the same type of I want to just draw the equivalence there. Okay, the same type of effect there, where you have the lone pairs on the chlorine stabilizing the adjacent carbocation charge. Okay, so ortho and para. Meta has no such luck. This guy here doesn't have the availability to be able to satiate that carbocation, because you can't directly dump electrons into that carbocation like you can here and like you can right there. Okay. All right. And so, you know what? Let's go back a few. I'm going to go back a few slides only to be able to have some drawing space, but we'll continue on in 1936. Okay, but let's just go back and give me this over here. Let's go back to the nitro group again and give me. Let me do nitrobenzene. And we will do. We'll do what? Let's do some bromination. Let's just do some bromination. That's very straightforward. Let's just do some bromination. Br2, Fe, Br3. Okay, and over time you will recognize the fact that this guy here will direct meta. Okay, so we're just going to write that answer down because we know it, right? We want to make sure that we always make sure, even though before we do the mechanism, if we know the answer, if we don't need the mechanism to determine the answer, let's just go into just writing down the answer, making sure that we don't forget that. Okay, Br. All right, and so I don't know why I drew this in the middle of the paper. I really needed the rest of this paper to do the work, but let me see what I can do here. Okay. All right, so let's just start off with, okay, so you have this down, so everyone copy this down, all right? So I'll just wait. Or I guess hit pause. hit pause or something, okay? Or check your pause and check your email or your Facebook or whatever. So write this down, and then I'll clear the screen and I'll go into what we're talking about. Okay, so nitro to meta bromo nitrobenzene. Okay, all right. Let's start up here, and we're going to start because you guys already know this stuff. I'm going to try and make it easy for myself if possible. All right. N O positive here, negative there. And I'm going to draw, you guys know what the activated form of this bromination species is, right? So we're just going to draw that because you guys are smart, right? We'll just do BR, right? BR, FE, and we don't need to draw out all those BR. 3. This guy here is going to be plus. This guy here is going to be negative. All right? And so, from here, we just take this pair of electrons here and swing. Now, notice where I'm putting my little pen icon here. I'm putting it in between the para and the meta because I know this bromine has to go meta. I know it has to go meta because I recognize this as an electron, as an electron withdrawing group, or as we call it in chemistry, an EUG. I'm sorry. All right, I don't know if that was too loud, but sorry to blow out your eardrums. EUG. All right, so anyway, this guy here is going to swing on out and grab that bromine right there. Okay, I'm not doing it from here to here, right? We have a substituent on this benzene, so now we have to determine where it's going to go first. Okay, so we have to have some sort of an idea. So we're going to put our pen icon right there, and go right there. This guy here will swing on up right there. Now we have no choice as to where to put it. We have to put it in the meta position. We have to, okay? Why can't I draw it connecting? Nitro. Okay. All right, so I'm going to keep on doing that. So the pair of electrons here swung out, and so it has to go nitro. It has to go meta from this nitro group here. So I'm going to go. Here's your bromine right there, plus your Fe Br4, the minus right there. And this guy here, right? So now we have to choose. Now we have to determine where to put the carbocation. Since this guy here swung on out from this pair of electrons, swung out from there, and we touched it right there, that must mean that this carbon right here must be electron poor now, right? So put the carbocation right there. All right. Is this something that's cool with us? Can we do this? Okay, remember that this is going to be an sp. Right now, it's going to be an sp3 hybridized carbon. All right. Is this going to be cool with us? Let's see. All right. If it's cool with us, that means we will never have a point where we can push this carbocation adjacent to that nitrogen. That just can't happen. All right. That's how we know that if we did that, that means then we know we screwed up. Okay. Let's see if we can do that. Okay. So allylic resonance right there. I'm going to draw the double arrows there just to show you that it's still resonance that we're talking about. Okay. N. Right there. Pair of electrons is now right there. This is now right there. This is now right there. Okay. Cool. There's your bromide right there. Okay, so that's good. So we have a carbocation that is next to the carbon that would be the violating carbon if we would have it there. Okay, so now can we draw more resonance? Absolutely. We'll do it right there. Sorry again about the insane looking lines, but doing my best. Especially wearing this these clothes. I can't talk about the clothes. It's just patently inappropriate. Not a bustier. It's not a bustier. It's hard. It's unfair to call it a bustier. You know, that's what it is, honestly. All right. All right. There's that. And here is your nitro group. All right. And there's your carbocation right here. Or those of you from the North Shore, it's a carbocation. All right, so there's your carbocation. There's that. All right, so at no time. So notice where the meta directors put the carbocations in their canonical forms. They put them crazily in the ortho, and para positions. Right, so the meta directors put the carbocations in the ortho and para direction in the ortho and para positions. Now notice if you go back and you want to do your resonance structures of your canonical forms of your ortho para directors, they will put those, where would you guess it? Indeed, in the meta positions, right? They'll put the carbocations in the meta positions while putting the substituents, indeed, in the orthopara positions. But the carbocations, if you want to draw out the canonical forms, will be in the meta positions, okay? So cool beans, eh? All right, let's just finish up this train wreck. All right. I'm gonna put this guy right here. Oh, well, let me just go back to this. Okay. So again, yeah, big deal. This carbocation here is adjacent to the carbon that would be the violating carbon if we would have it there. So what makes this so stable, or this so stable? Look at the extended conjugation. Okay, pi bond. So a pi system, a sigma system, a pi system. Okay. So it's sort of like an extended pi sigma pi over here. Okay, this extended conjugation there. And some conjugation there that's also extended. So we don't need no stinking adjacent carbocations to be able to have some stability with our deactivating groups. We can have easily some stabilization through extended conjugation, which is what we've been kind of selling this entire time. All right, so that's the reason why it's so stable. All right, there's my crazy hydrogen, and let's do this. Let's highlight one of the bromines here. FeBr. It's getting worse. Is my hand getting tired already? It can't get tired already. All right. FeBr3. All right. There's that. And as you might imagine, this guy here will swing on here. Grab that proton right there. Rearomatize this sucker. All right. And give us the nitro, the meta bromo nitro compound. Eek. That we so crave. All right, bromo. There you go. Plus HBr and FeBr3. Okay. So that's the whole mechanism. That's why it is indeed so stabilized, because you have some center conjugation there. We've done out the resonance. We've done out the resonance canonical forms here to tell you sort of why these things are so stabilized. Okay, and you can put the resonance brackets right there. Okay, right. Please write this over in your own notebook in a non-insane way, so it's more legible to you. Okay, so there's that. All right, let's go back to this other slide. All right. All right, so let's summarize the directing effects of some substituents. Strong activators. What makes them so strong? Well, you might guess it. Lone pairs, right? Those guys here have lone pairs of electrons on them. Okay, right? Strong. That's what makes them strong activators. This is why, like, if you were to have, like, let's just say on a ring, right? You have two activators on a ring, and they're not complementing each other. They are fighting each other. So if you have a strong activator and a moderate activator, which one would do the directing? The strong one would. The stronger out of the two would. So if you have a strong activator versus a weak, then the strong would activate. If you have a moderate versus a weak, then the moderate would also would activate. You would use those directing effects dictated by the position of the moderate activators. Okay, so that's how you want to think of it. So strong activators dump electron density into the ring in a very straightforward manner. R has to be alkyl group at this point, okay? Moderate activators. This is one level down from strong activators. Moderate activators. What makes them so moderate? They have something here called cross-conjugation, okay? What does it mean by cross-conjugation? That means that, indeed, you have some of the same benefits of electron donating ability from the lone pairs on your adjacent atoms, because you have some lone pairs there, but also, and I'm going to erase those things there. So you have this type of donation, but you also have this type of resonance as well. So these guys here have two types of resonances that are involved in in the directing effects of this molecule right here. So isn't that great? Don't you want more resonance? Isn't more resonance means more stable? It overall does, right? But that's not what we're talking about. That's not what we're talking about. We're talking about, I'm going to redraw this here, so I have to keep on, here, all right. All right, has not just this resonance, but also this guy here. That means that these two pairs of electrons are in something called cross conjugation. They both resonate into the ring and then outside the ring into this pi system right here. Okay, you have this a lot. You have this a lot with esters and with amides, secondary amides and tertiary amides as well. And depending on what the R group is, if the R group here is like, for example, like a, I don't know, a vinyl group. A vinyl group, right? If that's R's on R, but a vinyl, for example, that has the same type of thing. If you can push electron density into the ring and push it out of the ring using the same pairs of electrons, then it's going to be a moderately activated system because you won't have the complete dedication of a single pair of electrons to just dump electron density into the ring. You get it? This guy here just goes from here into there and just dumps electron density into there. And this guy here can dump electron density into the ring, then out of the ring. Okay? Cool? Get it? I don't know why I'm asking these questions. I can't see you. We're in cyberspace right now. Cyberspace. Ooh, that means I can like make my own. Like I could wear a jumpsuit and I'd be thin. Oh, the thought of that. Okay, so cross conjugation here. There's that, and that's what makes it a moderate activator thing. Okay, so there's that. All right, let's go on to this. Weak activators. What makes them so weak? Why weak? No resonance. Row resonance. Row. Roge, I rust my ruggy round. No resonance. Resonance. Sorry again about the crazy. I haven't been drinking. I'm really sober. Honestly, I'm drinking a cup of coffee. There, look, see? Coffee. I'm showing it to the microphone. That's good, Joe. All right, so no resonance. That's what makes them so weak. They're weak activators because they only use... What's this? Okay, thank you. Backup complete. They only use induction. Okay, only use induction. All right. So that's it. So methyl, ethyl, isopropyl, tert-butyl, blah 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 blah. So these all roughly activate in this, in the same orthopara direction. To roughly the same degree. What makes them different, though? What makes them different? This guy here, tert-butyl. This guy here is methyl. Everything in between. This guy here is big. This guy here is smallish. Smallish. All right? That means that these will all theoretically direct orthopara. But because this is so big, this might not direct ortho as much because you have lots of, as we say, this weird little thing here, you might have lots of steric hindrance here. So it might only, the major product might be only the para-directed species, whereas you have, when you have a methyl group here, you might have ortho or para, okay? In maybe roughly equal amounts, depending on what we're talking about. Depending on how big, if we're talking about methyl, well, we know what this is, but depending on how big the electrophile is, if it's a huge electrophile, it might still be favored more towards para than meta. But remember what we talked about before, there's two times as many ortho groups than there are para groups. All right, so depending on how big the groups are, they might be more directed towards para, but if they're moderate to small size, you'll get ortho-para mixtures here. But when you have a big group here, you'll have more major product, more in the para position. And again, roughly as you go down from large to smallish, you will have more and more ortho-para, more and more ortho coming in as this group here gets smaller, because you have less and less steric hindrance involved. Okay. So whereas you have two steric hindrance icons there, you might have one there, and you might have like a half of one here. That's not even something real. I just invented that right now. A half a steric hindrance. How's that? And then you have none right there. Okay, so that's cool. Weak deactivators. What makes them weak? Well, they're electronegative. They're electronegative, right? so you have that for deactivation, but you also have electron density. So while you are inductively deactivating, you are through resonance dumping electron density back into the ring. So you have this fight going on here, this really weird fight of induction versus resonance. Who will win? It depends. All right, it depends. So there's a fight between induction versus resonance. All right, 38. Moderate deactivators. What makes them moderate deactivators? Well, you have some. So what? Okay, let's look at moderate deactivators with respect to strong deactivators. What makes these guys here strong? You have to have something that's very electronegative. That's right next to the carbon of your benzene ring here. So you have to have something that has a what would be good if you had a stationary positive charge here like you have there, and you have this quaternary nitrogen salt here. This is also very positive right there. Again, it deactivates because it wants to it wants to pull electron density out of the ring and quench this positive charge. Right here, where X is either bromine or chlorine or fluorine, possibly even iodine, right? Again, through induction, this wants to pull electron density this way, okay? Because of all these pardons. Sorry about that. Doesn't mean to say that. Zoop, like that. Because of all the partial negative charges of the halogens right here, so you have a lot of electron density being pulled out of the ring because of these strong dipoles. Again, pulling this way. All right. But the point is that you have to have some electronegative element right next to the benzene ring, or just right to adjacent of that. Okay, so that makes it strong deactivators. But look at this. But what makes these things moderate deactivators, right, is that you still have carbon next to this thing, essentially, right? You still have something that's still very similar to the carbon that's in the ring. So you have these carbons next to it. All right, carbon here. Sulfur, again, in the same, sulfur here, is again very similar in terms of electronegativity. All right, so you have that there, okay? There's carbon again. But you have some resonance that you can pull up here. All right, when you have resonance that can pull up out of a benzylic position, let's see if I can squeeze the picture right here. Let's say you have this, and I'll just draw acetophenone for now. So you have this. This is the R here is this guy right there. Okay. Let's say you have this guy here. You can easily draw this resonance contributor right here, like so. All right. So again, this is deactivators not by electronegativity, so by induction. This is going to be by, again, deactivation by resonance. All right. O minus. So you have plus charge here and a minus charge. Sorry, it's really terrible, but you know what I'm saying, right? It's 6-membered. This is a 6-membered. This is the benzene. This is a carbocation. This guy here, you're pulling this electron density out of here, giving you that position right there, right? That this positive carbocation right there. All right. So this is why it's moderate deactivators, because you have no such electronegative element next to it, right? But you have the ability to have some resonance that pulls electron density out of the ring. Okay, so that's how they're different, sort of. You can do this for all of these guys right here. The sulfate group here, you have the same type of situation. In the cyano group, of course, you have that as well. You can pull this guy directly out of there. Okay. And strong deactivators, again, this is the gold standard of strong deactivators. It's just the I'm going to draw this. Why am I drawing? I'm drawing like this, like Blair Witch sort of a creepy star. Wow, that's getting even creepier, isn't it? Okay. Wow, that's creepy. All right. So this guy here, the gold standard in strong deactivation. Okay, but it can be nitro, it can be this guy here, some quaternary nitrogen here, or some halogen species off of there. Okay. So again, try to do your best to commit these type of things, not to memory, but just sort of understand why they are in where they are at. Why that trend is the way it is. Here's a thing I stole from Solomon and Friel's 9th edition of Organic Chemistry, a really great textbook, by the way. And you have a very similar one in your textbook, okay? I just like this one a whole lot, though. All right, strongly activating, moderate activating, weakly activating here, weakly deactivating, and here you go here. Now look at how it's cut down the middle. It's cut down by not by activating and deactivating, but by ortho-para directors and by meta directors. Okay. All right. Here's something. It's a really cool little feature that I should tell you about. And remember how we can't do Friedel-Crafts on things that have deactivating species here. Remember, said like, oh, you can do Friedel-Crafts as long as you have no deactivators, and there's that. But there's always the weirdness where you like we can do Friedel-Crafts if you still have a halogen on there. All right, so you can do that. So that sort of breaks that weird rule a bit. All right, and it even says in your book like you can't do Friedel-Crafts if you have deactivating groups on there. Right, and it's true, but it has to be moderate or strongly deactivating. If you have a weakly deactivator, you can do a Friedel-Crafts on there. But here's a better way to look at this Friedel-Crafts. Friedel-Crafts, you can do a Friedel-Crafts as long as you have only ortho-para directors on your molecule. So you can, yes, indeed, do a Friedel-Crafts when you have fluorine, chlorine, bromine, or iodine on there. Anything past that, this guy here, Friedel-Crafts here, no. Friedel-Crafts, no here. Friedel-Crafts, yes. All right, there's that. Okay, so you can do Friedel-Crafts as long as you have an ortho-para director, but no meta directors. And that, if you think of it that way, with just for Friedel-Crafts, then you won't get that wrong ever. If you think of Friedel-Crafts as like, oh, I can't have a meta, I can't have a deactivating group on there, and if you end up seeing a halide, you'll say, oh, I can't do a Friedel-Crafts on that because it's deactivating. But if you think of Friedel-Crafts as being able to be done on a benzene that only has ortho-para directors, you'll be totally fine all the time and get always the right answer. Okay, so cool beans, huh? Nice little feature. That's why I wanted to add this little table in. I think this very clearly states that. Okay. For the compound below, determine whether the group is electron withdrawing or donating. Also determine if it's activating or deactivating and how strongly or weakly. Finally, determine if it is ortho, para, or meta directing. Okay? So, this guy here has a lone pair on it. Right? Lone pair on it. Okay? That means you can dump electron density into the ring right there. Right? And so, and you also have some alkyl groups over here like so. But you also have the ability of it to be able to do some cross-conjugation. So according to this, what would this amide group be? Is it ortho, para, or meta directing? Well, let's look at this guy here. So let's look back to here. This guy here is a moderate activator, because even though you have an electron, you have a electronegative group on it, it has lone pairs on it, so it could donate electron density to the ring. And it's also cross-conjugated. Even though it has an alkyl group on it, so this is more the correct answer right here, it is a moderate activator because you have some guys right there that can dump into the ring, but you also can dump electron density out of the ring, or pull it out of this region right there. So this guy here would not fully be conjugating into the ring here, but would also be resonating or conjugating outside of the ring. So it's a moderate activator, and what we would say for a moderate activator, it would more direct ortho-para, right? And that's the right answer. So it's activating, and it's a moderate, and it would direct ortho-para. But what do you think overall this guy here would direct? Do you think that guys here think it would direct only ortho, only para, mostly ortho? I won't wait for your response, because I know I'm just looking at the screen right now, not talking to really anybody. But here. This is a very large group right here, right? So there's lots of steric hindrance going on right there. Okay, so while it does direct ortho and para, the majority of the product would be para, because of the sterics that is associated right with this group right here, and it would sort of favor the para, because you would have a lot of these ortho positions blocked as much as possible, or they'd be blocked because of both the methyl right there and the acyl group right there. Okay, so that would make it more para directing, but theoretically it would be ortho para directing. Okay, get that? All right. The directing effects of all substituents attached to a ring must be considered in an EAS reaction. So electrophilic aromatic substitution. Predict the major product for the reaction below. Explain. Okay, so you have nitro group here. So nitro group here directs meta to this nitro group. I'm drawing meta to this nitro group. This guy here is meta. We can also circle it. So meta positions here. Okay, so there's that. But the CH3 group, the alkyl group, directs ortho-para. So this guy here is meta to this, but ortho to that. So this is ortho there. And so this is ortho and meta, both here, and para is right here. But you can't put something in the para position because the nitro group is already there. So your overall answer is going to be, overwhelmingly. Why am I drawing this leaning over? I think it's because. Is this better? No. Let's say CH3. No, it's not better at all. All right, NO2 and BR. Okay, BR. It's going to be overwhelmingly this. Why? Because the para to this is not available because you already have a substituent on there, and this guy here is both the meta position to this and the ortho position to this guy here. So this guy here these guys here are complementing each other in terms of their reactivity and their directing effects. So this guy here is ortho. This guy here is meta over there, and that's why this guy here goes these positions only, because they are complementary positions. Okay, that is ideally what you hope for and try to design into your synthesis all the time. All right, so that's the reason why that is that reaction. Take a sip of coffee here. Hold on for a second. Oh, that's good stuff. Let's call it coffee. It's coffee, I promise you. Okay. So predict the major product of the reaction below. Explain yourself. Okay, so this guy here is ortho-para director. This guy here is also ortho-para director. Crap, right? Because, okay, ortho here to that guy here and para to this. So that's not going to work out for us. And this guy here is also ortho-para director. So ortho and para to the methyl is also that which is also not available to us. Okay, so now we have essentially four possible ortho positions. So what do? Go with the stronger one. We go with the stronger position right there. So it's obviously going to be, not obviously, I won't say that again. It's going to be the stronger activator, right, will beat out the weaker activator for its directing group ability. So NO2. There's that. Okay, cool. Again, and so this is an example where you do not have complementary directing effects. You have things that are non-complementary. They fight each other, and so you have to at that point pick your battles essentially. Okay. So you always want to go with the stronger one here. All right. Consider sterics in addition to resonance and induction to predict which product is major and which one is minor. Okay? Alright, so you have this isopropyl methyl here, isopropyl methyl benzene right here, and you want to do nitration. So it's either going to go there or going to go there. Let's look at the reactivity here. This is an ortho-para director. This is also an ortho-para director. So ortho to this and ortho to this is indeed both that, and para to this. Para to this methyl is this. Para to this guy here. Okay, so I'm sorry. So ortho is here and here to this guy, and ortho is here and here to this guy. Para to this guy here is here. Para to this guy here is right here. Okay, so you have 3 points of reactivity. All right, considering sterics, in addition to resonance and induction, predict which is the major and which is the minor. Okay, which one do you think? We're only giving you these two choices right here. Which one do you think, here or here? And obviously, here is going to be this guy here is going to be the major product right there. Why is it? Because if all things being equal, and they have relatively the same effect, relatively the same magnitude of effect to directing, which they sort of do, all right, you'll want to pick the one that has the least steric hindrance next to it, which is going to be this guy right there, not this guy right there. And indeed, this absolutely does happen. All right. So this is why this one here is the major product here by I'm sure 20 to 30 or 40%. All right, this guy here is not observed. Why is that not observed? Because again, sterics plays a humongous part of this thing here. Okay, you'll have sterics from here and a little bit of there, but mostly isopropyl is a pretty big group. It's almost as big as tert-butyl when it comes to benzene substitution. Okay, even though these are both doubly reinforced, it's a very hot area for substitution for these groups here. It's still not, so it's not going to be the best thing to do though for best place to choose for sterics though. Okay. All right. What reagents would you use for the following reaction? Okay, so you want to put something here next to the tert-butyl group, which is again, it's a gigantic group. So how could you get anything right next to it? You could force it. You can force this thing. Okay. Is there a way to promote this going from here to here? Yeah, sure, not in one step, but absolutely. There's a way by using our cunning. All right, we could really stack the deck. Okay, so how about if we put something here para to this guy here, which is very easy to do because this guy here is huge. It won't direct anything ortho. It'll direct it para because of sterics. Install some blocking group, right? Brominate. Maybe something here that will direct meta possibly. Imagine if this blocking group here direct meta. This is the meta position to the blocking group. That'd be good here. And this guy here would be orthopara. So this guy here would be doubly enforced. So blocking group here, brominate at this position at that point, then unblock to give you that guy here, to give you this overall species here. Can we do that? Absolutely. Okay, why can't we do this? How can we do this? Remember back a few slides ago? And we said, here's how you can do some sulfonylation here using fuming sulfuric acid. Again, not sulfuric acid that's really pissed. It's just sulfate dissolved. The sulfate here this sulfur dioxide that is dissolved in sulfuric acid, right? That gives you this guy right here, and you can clip this guy off here by using some dilute sulfuric acid, not fuming, but just some dilute sulfuric acid. So sulfuric acid in water. Okay. You can take this guy here, use fuming sulfuric acid to do your sulfonylation. It'll go selectively to para, right? Because ortho here is so crazy sterically hindered, it won't go there. Then you do your bromination. Then this guy here will direct meta. This guy here will direct meta. Right? This is a meta. This is meta to this sulfate group here, and ortho. Right? This is ortho to that alkyl group. So you have a meta director here and an ortho para director right here. The para is blocked because of the sulfate. So now you have the ortho meta substituted bromo species here. So now once you get that, you can now just jettison this guy here by using dilute sulfuric acid and giving you your overall product right there. Again, this is the kind of like weird like Sudoku like puzzle, or like weird like sliding numbers like puzzle you'll have to do when you look at the syntheses of of benzene rings here. It's its own little art. It's its own little offshoot of total synthesis that you'll have to definitely master. Okay. All right, reagents for monosubstitution aromatic compounds. Bromination, chlorination, nitration, fuming sulfuric acid, Friedel-Crafts alkylation, Friedel-Crafts acylation. All right. Iron or zinc will reduce this guy here to the amino group here. This guy here doesn't do anything except if you want to go back here, you want to use some dilute sulfuric H2SO4 and some H2O right there. All right. This guy here doesn't go on to do anything else. This guy here is primarily used as a blocking group, by the way. Okay, so alkylation, go over there. And then you can do like all your other kind of crazy stuff that you want to do. You can do your brominations. You can do your chlorinations. You could do your potassium permanganate in heat, or remember your Jones, your sodium dichromate and sulfuric acid to give you your carboxylic acid thingies there, right, too. You can also use your Clemenson reduction to give you, and use some zinc amalgam and some HCl in heat to give you this species right there, okay? So you have all kinds of cool stuff that's just opened up to you, okay, in terms of functionality, changing functionalities, right? All right, so here's a very cool little thing here. Let's just say you have a functional group that you have on there already, and you've got yourself into a bind, and you need to be able to to put something on orthopara when you have a meta director, or meta when you have an orthopara on there. You might not totally be hosed all the time, but if you have the right groups on there, you can do some quick transformations, okay? If you have a nitro group on here that's a meta director, you can just use some zinc and HCl, right, to convert it to the amino group here, which is a very strong orthopara director. Almost, it's as strong as your phenol, as your OH group over there, okay? Or if you have this guy here, if you have your alkyl, phenones, you can treat this guy here with Clemenson and give you an orthopara director, which is cool, huh? Again, going the opposite way, if you want to go orthopara to meta, think about taking your alkyl group here and then burning it up, if you can, right, with some Jones or with some other exhaustive oxidation procedure to give you the meta direction. Or looking at this alkyl group here, if you want to treat it with excess NBS, you can get the tribromo compound, which is a meta director, which is also a deactivating group as well too. So you have all kinds of nice functionality there. Okay, so think about that all the time, right? When you're going forward in your syntheses. All right, so there's no need to always like reinvent. I was gonna say like reinvent the horse, but that doesn't. Horses have already been. Reinvent the wheel or kill or beat the horse. I don't know. I think beat a dead horse. I think that's what I was going. I mixed my metaphors. All right. So yeah, there's no need to always go back. But oh crap, I need to put something else on. I meant to do something else and not that. Oh, I maybe can convert it. So just think about it, okay? But give yourself enough time to think about it. All right. So there are limitations that you should be aware of for some of these electrophilic aromatic substitutions. We've already talked about the Friedel-Crafts, which we'll talk about again, okay, a little bit. We'll just touch upon that one final time. But nitration conditions generally cause amine oxidation, right, leading to a mixture of undesired products. Okay, why does that happen? Why do we not get this guy here when we want to do nitration things there? Okay, well, because remember what is the thing that we're using when we're doing a nitration procedure? We're using this guy here. We're using, sorry, let me just start clean slate again. We're using, right, this guy, this nitronium species right there, okay? We're using that guy, all right? And if we were to do this, we won't just get the orthopara direction, because while you might get some of this will not be the major part. Why won't you have this? Because you have a far more nucleophilic pair of electrons that is much more interested in that yummy electrophile, right? So what you'll end up getting is not this amino thing, right? You'll end up getting this guy here, which again is a useful reaction, but not for what you want to, not for this purpose. Right? It's another type of useful reaction, okay? I believe you can make N-nitroso compounds here this way. I believe. I gotta double check on that for you guys. Make this weird intermediate right here, okay? Okay, not very stable, right? There's charges right next to it. You'll have to like deprotonate this guy here, and then this will go over. But this is where it starts, right? And then you do all kinds of weird chemistry here. But again, this will not react in this way as an orthopara director. You will end up doing a lot of oxidation to this compound, to this amino group right there. Okay, so make sure that you never try and do some nitration when you have a free amine there. Okay, it's not going to happen. It's not going to happen. All right, Friedel-Crafts, we know this, are too slow to react, right, when you have a deactivating group present on the group. But let's not say deactivating group. Let's say when you have a meta group, when you have a meta director, you have a meta director on there. Okay, let's just say that. Okay, so this guy here doesn't work, no reaction. So Friedel-Crafts alkylation or acylation here when you have a moderate or a strong deactivator. With a weak deactivator, like halides, you can definitely do that. Okay. Using anhydrides and Friedel-Crafts alkali. I love anhydrides. Okay, there's a lot of really cool anhydrides to use. All right, let me show you. And so what's an anhydride? An anhydride is the result mostly of 2 moles of some acetic acid, some carboxylic acid, when treated with some heat, will give you this weird looking ester looking species right there, right? Plus H2O. Okay, so where does the water come from? The water comes from, and we'll go into this mechanism more, and I think in the next chapter actually, but just to give you an idea where overall it comes from, I'll just draw it. I'll just draw some stoichiometry for you. Here is the result. H2O. That's how you get this. That's how you get this water. Okay, and this guy here attacks into this carbonyl, kicks off this what would be an OH2 group eventually, to give you this guy right there. Okay, and the driving force for this reaction is a nice entropic effect where you create two particles here from one particle here. You liberate some water, and you have your acetic, in this case here, your acetic anhydride. Okay, so using anhydrides in Friedel-Crafts alkylation, or Friedel-Crafts acylation. All right, let's just get a clean slate. All right, and so here we can do a few different things. We can use, let's use, well, you can use Lewis acids, but I've seen more of these Friedel-Crafts acylations happen when you use either HF or polyphosphoric acid. I don't think your book actually has this as a thing. I gotta like double check it one more time here, but I don't think they use it. But PPA is polyphosphoric acid. It's a crazy strong acid. Okay, and this guy here is your acetic acid. Okay, and so what you end up having here, and PPA is just one acid that you can use. I'll try and get some alternative acids for you as well. I don't know if you can do this by Lewis acid. I don't believe you can though. Right. So your overall reaction is going to be that if you're using this acetic anhydride, whatever this guy is here, it's going to be that over here on that. Let's put a weird star. Oh wow, that's a pentagram. Crap, I'm not a devil worshiper. Not that the devil worshippers. I'm trying to be inclusive here. It's not a pentagram. It's just a star in a circle. Yeah, whatever. Okay, so there is your acetophenone with your weirdly pentagrammic type of substituent on there. All right. So how does this happen? You take your very, very, very strong acid, and we'll just say this. We'll just say this. There is your anhydride. We will say that this H plus belongs to a crazy strong acid. This guy here will grab that proton right there, like so. All right. And so what happens here? You make this crazy thing. All right, and you know that oxygen does not want to be positive at all whatsoever. So this guy here wants some electron density. So here's where you start pushing electrons from. You start pushing electrons all the way from the other oxygen, the other carbonyl's oxygen. This guy here swings on down. This guy here swings on up. This guy here swings on up. And just look what you've made. Okay, look what you've made. All right, you've made this guy here. I'm going to draw this guy here in the same angle that it's reacted, okay? Just so you can see how clearly positive this thing is formed. Look at what you just formed. You formed a mole of acetic acid. A mole of acetic acid, because this guy here is now a new double bond, right? This guy here is now a single bond, all right? But what you formed right here, your old friend, the acylium ion, right? And 1, 2, and I'm not going to draw this sp hybridized carbon as a bent thing. Okay, so there's that. Hey, there you go. Okay, ready? So there's that. So this is your acylium ion that we talked about, I believe, on Thursday. And here's your acetic acid byproduct. Okay, now you go forward with the exact same type of Friedel-Crafts acylation procedure that we talked about already. Okay. And we'll just use benzene. We don't have to use any substituent effects. So we're just trying to do the chemistry here. All right. There's that guy right there. This guy here swings on out. grabs that. This is a crazy hot electrophile. There's that. There's that. There's acetophenone for you right there. There's your carbocation as is. And then you can have either water or some other conjugate base species reform your. Let's just use water here. There's always water sort of hanging around. All right, to rip off that proton here to reestablish aromaticity and give you your satanic acetophenone species that we've made inadvertently. Okay, so there's that. All right, are we cool? Using anhydrous as Friedel-Crafts alkylation procedures. Okay, put this on pause. Make sure you can redo this and like this. Here's a favorite problem of mine, an absolute favorite. Okay, it's not. This is plain old acetic acid. Pretty boring, if you ask me. So let's do something else that's really awesome. Okay, do this. Use this anhydride. Use this anhydride. Use this guy here. This 5-membered ring anhydride. I love this. I love this. I love this reagent. When you use this with benzene and PPA. All right. And then I'll give you the answer. All right. It'll be obvious. But this is not going to be. The answer is not going to help you. The answer is going to be your goal. Okay. I just want to make sure that you know this. Okay. So you're doing an acylation, so that does not change. But remember how it was in the prior slide? You liberate one mole of acetic acid. You liberate 1 mole of the acid here as well, but it's still tethered to the rest of it. So 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, and 4. 1, 2, 3, 4. How awesome is that? Look at that! Look at that craziness. Do it with this mechanism and see if you can get to that. Okay, it's a very cool mechanism. The same exact mechanism as we just talked about. Okay, but it's a little different of a substrate for this reagent. Okay, a little bit different structure of this reagent. Okay, so make sure you take that into account. All right, no, it's no harder than the other one. All right, design a synthesis for the following molecule starting from benzene. Okay, let's go into this. There are several ways to do this, and here's just one way that I can think of. Okay, so from benzene, can we put anything on here? Do we know any way to put a carboxylic acid directly on here, and then put another carboxylic acid on here? Okay, can we do that? We know of one way, right? We could brominate. We can do an EAS bromination, Br2 and FeBr3. Maybe do some what do you call it? Grignard chemistry. So throw in your magnesium, and then bubble in CO2, and then you get your carboxylate followed by the acid. Followed by acidification. That will give you that carboxylic acid. The problem is if you start off with a carboxylic acid, right? Start with the carboxylic acid, then you're going to have, then you're going to have a problem directing orthopara, right? And if you're doing another carbon directing orthopara, that means you're trying to direct orthopara. I'm sorry, you're trying to direct orthopara, yes, with a meta director. But before that, you're trying to do Friedel-Crafts chemistry when you can't do Friedel-Crafts because you have a deactivator on there. So we need a different tact, okay? How must we do this? All right, let us do this. Let's do it this way. Let's us put. How about we do this? How about we put? This guy on here. Yeah, we can do that. Let's do this. Yeah, let's do this. Yeah, let's just do it this way. Let's do ethyl chloride. Let's do ethyl chloride and AlCl3. That will give us this guy here, the ethyl benzene right there. We want this guy here to go meta, right? So can we do another? If we do another like Friedel-Crafts, even if we use methyl, right, it would still go orthopara. We wouldn't have exclusively this ortho. We want exclusively ortho. So what must we do? I think what's sort of heading for us right now, right? Let's use that crazy fuming sulfuric acid procedure that we learned about. That's really kind of cool. Okay, H2SO4, H2SO4, sulfuric acid. Okay, blocking group. Cool, eh? All right, we'll do that. SO3H. We'll do that. All right, so then we can put on the other alkyl group, right? We'll just put on the other methyl group or ethyl group here, and then we'll take that off, and then we'll use Jones to take everything down, right? Isn't that cool? Wrong, can't do that. Remember? Meta director, yes, true, but also deactivator. So we can't do any Frida Crafts. That's closed to us. But what's not? That's the only thing that's closed to us. There are plenty more fish in the barrel. Fish in this, like shooting fish in the barrel. Let's do this. BR2, FeBr3. All right. Look at that. We can do bromination, and then that'll definitely go. That's not Frida Crafts, right? We'll definitely be fine. Br, SO3H. There you are, right? That's cool. Now we can go. Now what we have to do is we have to get rid of the sulfate group, because what we're doing next, we're going to do this something else next on this thing. Okay. So H2O, H2SO4. All right. And then we will have that guy, H2SO4, there's that, BR. So what do we do next? Alright, here's what I would do next. I would take this guy here, first step, make this guy here a Grignard, magnesium and ether. Second step here, bubble in CO2. Bubble in CO2, which is the best thing in the world. We've talked about this. Make this guy here a Grignard, and Grignard will attack the CO2 and make the carboxylate. Right? CO2 minus. It's going to be the minus. There's no acidification there, right? All right. So now we get to the final step. Get this guy here. Dr. Jones. Sodium dichromate or Jones oxidation. Once you have that position, you will have your product. You will have your final product. Right? Coolness, right? Do you know another way to do this? Can you do it any other way? What do you think? If you don't like this way, if this way is too cool for you and you want to be less cool, fine. Use formaldehyde. Use formaldehyde to make the alcohol there, and then Jones it all down, or up, or whatever you want to say, or an epoxide. Put some of the carbonaceous group on there to be able to oxidize everything away, right? To give you your diacid. Okay, there's plenty of ways to skin this. To skin the cat. Skin a cat. We'll skin a cat. There's a metaphor for you. All right. So there's that. When designing a synthesis for a polysubstituted aromatic compound, you use retrosynthetic analysis. We talked about this before. For everything, all right? Okay, so design a synthesis for this molecule below here. If you have a nitro group on here, if you look at this nitro group here versus bromo versus this guy over here, these guys, a nitro group is so strong. It really does dictate lots of things that you can and can't do. Like it will only direct meta. It will deactivate the ring such that you cannot use Frida Crafts. So think about not putting the nitro group on until the very end if you can deal with it. All right. So just think about that. Try that way. Okay. But what I want to say to you is this. So I'm telling you, I came about this answer pretty quickly because again, I know the notes. I've done this lecture before. I know this synthesis, but there's no necessarily, very rarely is there any one really right answer. Okay, so I just said don't do that, until the very end. But I'm sure some of you guys can prove me wrong, or show me a different way to do it, which I would be more than happy to look at. Right. So again, it's not like it's just the end all be all because I said so or because some textbook said so. All right. But here's how I would go about it. I would attach this guy here last, and then once you have this, well, then that's easy to sort of deal with. Okay, bromination, do your Frida Crafts acylation. Look at this. Here is a book. Here's a textbook example, literally from your textbook, right? That gives you Frida Crafts acylation, right? using this quote unquote this weak deactivator, right? But again, it's an orthopara director. Okay, this guy here will direct specifically para. Okay, because again the size of this is pretty big. You might get some ortho, but I get mostly para because it's so big. And then the nitration step right there. Okay, so pretty cool stuff, right? Nucleophilic aromatic substitution. Changing gears here a little bit if you're changing gears. If you're driving an automatic, gears are something that helps you, well, whatever. Okay, so nucleophilic aromatic substitution, or as we say, NAS. All right, as I go off screen. All right, consider the reaction below in which a nucleophile attacks the aromatic ring. Okay, do you know how this mechanism works? I think you do. It's not too terrible. Okay, is there a leaving group? Oh, sure there is. This bromo is leaving, obviously, right? Because it's left. It's not there anymore. It didn't change magically into some hydroxide. We see the hydroxide source right there. Notice the heat. Notice the acidic part of it, okay? So what happens here? It's actually more straightforward than you think. It's not electrophilic aromatic substitution where the benzene acts as the nucleophile here. The nucleophile here is indeed a real honest to goodness nucleophile, the hydroxide. Aromatic rings are generally electron rich, which allows them to attack electrophiles. To facilitate an NAS, it must be electron poor. Why? Because it has to accept a pair of electrons from the hydroxide. The ring must be substituted with a strong electron withdrawing group. 9 times out of 10, you'll see the nitro group being the thing that is going to be it will be the group that will help this reaction along. There must be a good leaving group like bromo or some sort of a halide. The leaving group must be ortho or para to the withdrawing group, okay? We will look at the mechanism and explain why, okay? Parachloronitrobenzene. You have hydroxide attacking in right there. This guy here can go in. So as this guy here attacks right into where that chlorine is, you will form an intermediate Meisenheimer complex. It's just another sigma type of complex, but because Professor Meisenheimer, which sounds sort of like a weird villain, because he discovered it, he gets named after himself. So there's that. So this attacks in right there, gives you this pair of electrons right there, which can then be pushed into the ring here and into this carbon right there. But as you push this into this carbon right there, you will see that you can not just stop here, but push this all the way in to this carbon nitrogen group here, and then have this guy right there. All right, giving you this species right there. And then when you do this whole cascading thing back out of the nitro group and back into the ring, zoop, 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 and kick off, you end up getting your overall final compound, which is pretty cool, right? It rearomatizes all by itself. You need no such thing to rearomatize the ring. All right, so again, practice this mechanism. Notice this guy here is, notice these guys here are para to each other, right? These are para to each other. These are not ortho, these are not meta to each other, these are para to each other, right? All that, you have to have para. If you have meta, look what happens, okay? If you have meta, look what happens. You have no such luck. Let's draw it out really quick. And I won't be as nice as drawing on all those little details, but I'll show you the detail that means something to you. All right. Bromo. Here's your meta nitro. I'll draw this out just so it's easier to see when I draw out the entire beeswax. Okay, so hydroxide, 70 degrees. Slam. Okay, this guy here will slam into here. You ideally would love to push the electron density from here into this out of the ring somehow into this nitro group, but you cannot. There's no way you can get to this ring. You can't get this out of here because it doesn't work that way. The best you can do is like go from here and push it down to here, then maybe push that down to here, and then you give you this. That will give you this sort of this form of the Meisenheimer complex. OH. This guy here is still going to be waiting. Nothing happening there. All right. There's no way I can push this pair of electrons into this ring at all. I can't even. I'll make another run at it. I'll just run fast. I can't push. There's nothing to push in there. It would have to just go back up to here. Or the way the book does is that you can do it back up to where it is there, or you can push this guy back up to here. Okay, but so this is what happens. You have no such luck here. All right, this does not happen because you have no stabilization. So you do not get the hydroxide there at all. Even though I showed this here, I'm showing you that you can't push the electrons back into there. All right, so this attack never happened. You didn't see a thing, turn around, just go home. You're drunk, okay? Doesn't happen, all right? So this thing does not exist, right? Because you have no such stabilization, so there's no reaction here. So whenever you want to do this sort of nucleophilic aromatic substitution, you want to make sure you have either the bromo being in the, the nitro being in the para position, or the orthos. They both work out fine that way totally. Okay, so let me take another sip of coffee here. Hold on for 1 second. If you have excess sodium hydroxide, like you will have for this reaction, you will indeed do your wonderful NAS reaction, but you won't end up with the hydroxide. You won't end up with the OH. You'll end up with this phenoxide species. Make sure that you throw on some acid to get your phenol back, or if you really want to be the cool kid on the block. All right. Think about doing some hot Williamson ether action. Imagine this. Can you just figure this? Right? How awesome would this be? If you guys were to make this guy NO2. Look at that. Ethyl. This ethyl species here, instead of protonating it, just throw in ethyl, I don't know, ethyl chloride, ethyl bromide, whatever you want to do. Cool, huh? You can do that instead, and just have your end game not be the protonation event, but have it be the Williamson ether event. Okay, to do that. Okay. Or hell, wow, how cool? How else cool do you want to be? Do you want to do this? Do you want to throw in some epoxide? Imagine that. We have maybe some R group over here. All right. Imagine, oh God forbid, you put some Barry Sharpless chemistry right on there, right? Get you some nice some very stereo specific epoxide species there. Then you can really be able to induce some nice stereochemistry there to give you some nice a highly ordered system that would give you some beautiful continuous stereo centers that you might be able to deal with and build some complexity into your molecule. How great is that? Right? You have all kinds of things that you can do here. A lot of things here that are very much opened up to you. All right. Without the presence of a strong electron withdrawing group here, this is now a different topic, elimination addition. We're almost done. Just hold on. Then you can go back to looking on the YouTubes for something else that's a little bit more titillating. All right. Without the presence of electron withdrawing groups here, you have no such luck here. Okay, you have no such luck. So NaOH with 70 degrees, for example, like you did before, does nothing at all. But if you use significantly harsher conditions, like 350, like boil the crap out of this thing, heat it up and heat it up and heat it up, you will get something. Notice the heat here, okay? The heat here is insane, okay? So in Celsius, water boils at 100, okay? Just so you'll know, all right? So if you take NaOH and throw it into 350, you will get this. Indeed, you will get some of this hydroxy, some of this phenolic species formed, and probably in pretty decent yield too after acidification. Again, 350 degrees, not something that you can reach very readily. Okay, all right. The reaction works even better when a stronger nucleophile is used. All right. So you use sodium amide followed by liquid ammonia. And giving you, in the second step here is going to be the protonation event after that. How could this possibly happen? What's the mechanism that this goes by? So you get this and this, okay? When you treat this guy here with sodium amide followed by liquid ammonia, right? You get that guy, right? And followed by your protonation, all right? So your regiochemistry or your regioselectivity cannot be explained using your nucleophilic aromatic substitution. So there must be some other mechanism at work here. So using isotopic labeling experiments help us out here to sort of discern what the chemistry might go on here. carbon with the asterisk is a C14 isotopic label. Okay, that means that like when I look at my carbon NMR, all right, this will show up as a different peak altogether. And even also into my proton NMR as well. Okay, so this will show up as a different peak or no peak at all, depending on how your NMR is tuned. Okay, so the NH2 first acts as a base rather than a nucleophile. Then it acts as a nucleophile. Okay, so this guy here, you get a 50-50 mixture of the isotopic event where this guy here adds directly to this carbon here, which is this carbon here, and 50% where it adds to this adjacent carbon right here, or to the other side, right next to that isotopic carbon. 50-50. What could possibly be the mechanism here that might not be too ridiculous? Well, imagine this guy undergoing some sort of a weird, crazy, high-energy E2 reaction. You pull off this quote-unquote, I'm using air quotes with when I'm recording sound, so if you can hear my air quotes, that's really fast air quotes, you can just hear that, okay? I know I should have been like a 1930s like a radio guy, huh? I know. It's a gift. What can I say? It's a gift. I don't want to brag, but it's definitely a gift. Okay. So you take your strong base here, you pull off your beta proton here. This guy here swings on down, kicks off the chlorine, and makes something called benzene. I know. You read it here first, folks. It's a benzene with an alkyne species. Look at those crazy bonds right there. Do you believe that? I don't believe that drawing. It's something that we draw to make it not too ridiculous, but it is a ridiculous drawing. Why is it so ridiculous? You know the hybridization of those those sp hybridized carbons, right? They're not bent in any way. They're not 120. They're 180. All right, that's it. That's how it goes. So because we know that benzene cannot allow for those things here, we draw it this way because everyone draws it that way, and we want to be as cool as everyone else. But the benzene triple bond resembles more closely an sp to sp2 overlap than it does any sp. And imagine this guy here being sort of a diradical-ish, but not really. Okay, but it has some. It has some radical. It looks like it might be some radical character in there. Okay, so it's not a p overlap bond at all. It has some. Imagine it being sort of being some sort of an adjacent diradical. All right, so that's how to think of it that way. Okay, but again, this is such a specific thing. If you see this guy, if you see chlorine or bromine with sodium amide followed by liquid ammonia, you know what the deal is going to be. All right, so make sure that you don't sort of miss that. Okay, so the elimination addition and the nucleophilic aromatic substitution are very different from electrophilic aromatic substitution. Okay, just make sure that you sort of categorize those in your heads a very, very, very specific way. All right. So anyway, you have this guy here. The first mole of this acts as a base, as a very strong, crazy strong E2 type of base. All right. And then what happens after that? Then you have the first step was the elimination. Now comes the addition part of it. This guy here adds to this guy here, flipping out some electron density out to the outer edges of that system right there, and then reprotonating again using, remember the other reagent here is liquid ammonia. This guy here readds there. You have a carbanion there, which then gets protonated by liquid ammonia, and this happens for both this side of the benzene. I'll just erase this. This happens for this side of the benzene, and also for the other side of the benzene as well, right? That's why you have a mixture of a 50-50 mixture here. Again, it has to be pretty strong base and pretty hot to be able to do this kind of thing. All right, so there is elimination addition part of this chapter. What other crazy things can you do? This is one of the things that helped us determine that that benzene, quote, right, sort of existed. You can actually take benzene and do some cool Diels-Alder chemistry with it, because this guy here is the diene, for example. This guy here is the diene-O-file. So you can definitely make the Diels-Alder cycloaddict. Isn't that an insane thing to draw, right? But it's cool. It works out. It works out totally fine. You can absolutely do that, and this is available to you. So please feel free to implicate this benzene in your favorite Diels-Alder reactions with your cyclo editions, to give us really cool cyclo editions. Okay, that's a very cool thing to be able to do. All right, and with that, I do thank you for tolerating my on-screen and off-screen antics, right? And enjoy this recording, and please replay it, and again, have this done and read and digested, by Monday. Okay, we'll start fresh on chapter 20 on Monday. All right, thanks for your. Here's my little screen recording icon, guys. How's that for low tech? All right. So, yes, I'm using QuickTime. How cool is that? All right. So again, thanks for your attention and cooperation. And again, have a great weekend. Study hard, and see you Monday. Ta-ta.